So table 12.2-1 from ASCE 7 is a very important table for seismic design of wood structures. Seismic design of wood structures is almost always designed using the equivalent lateral force method, or ELF for short, ELF. And in that methodology, it's required to have defined seismic systems with associated seismic coefficients. And this slide highlights the common lateral wood systems that are available in table 12.2-1 of ASCE 7. Now, the most prevalent wood lateral resisting system is the wood frame shear wall, and you see in item 15 light frame wood wall sheathed with wood structural panels rated for shear resistance. Table or item 17 then are light frame walls with shear panels of all other materials, and those other materials commonly would be gypsum, stucco, structural fiberboard, and materials like that. And then item 6 under the cantilever column system, examples of this would include a post frame structure where the posts are embedded into the ground, and those are typically one-story structures, and you might also get some pile supported structures in this group as well. But there are two things about item 15 that you should be aware of. One, there's an errata to ASCE 710 that clarifies that this light frame system is applicable only to wood structural panels rated for shear resistance. There's a typo in ASCE 7 where steel sheets were also permitted on wood frames. And steel sheets are permitted and recognized for steel studs, but they're not permitted for wood studs. And the second thing that you want to know is that this table contains a height limit. So if you're doing a seismic design of a wood structure using a wood frame shear wall, your height limit is going to be 65 feet. And in contrast, if you have a light frame shear wall that uses other materials like gypsum, the height limit is going to be 35 feet. And you should also be aware that this category 17 is limited to seismic category D within ASCE 7. And so we'll talk about some additional limits later on in the program as well for that system. But let's talk then a little more specifically about the calculation method. Most wood frame, wood structural panel shear walls would be calculated or would calculate the period using equation 12.8-7 in ASCE 7. And the reason we mention this is because the language in ASCE 7 mentions that this formula is specifically applicable to wood frame. And as an example, it states C sub T is applicable for all other systems. But we want to clarify that this is indeed also applicable to wood frame. In other words, wood frame structures fall into this category. In ASCE 7, the term structural height was clarified as being measured from the base. And this clarification was put forward to address light frame on a rigid podium per the two-stage analysis process. So the top of the podium is the base for the light frame structure above, and most importantly, the structural height of the light frame structure is from the top of the podium, not height above grade or lowest point of access. So for light frame, the structural height limit is 65 feet. So if you apply this equation to different heights and buildings and structural heights, it's the height from the base, or maybe the top of the podium, to the highest vertical lateral force resisting element. In the case of pitched roofs, which you often get for residential structures, it's going to be the average roof height. So it's the base or top of the podium to the average roof height. So if we were to apply the equation to a typical wood frame building, so that C sub t equals 0.02 and the structural height varies, this table shows the results for those different heights. And this shows that wood frame structures are typically going to have a very short period. And in the shake table test that was just shown, that was a height of about 56 feet. And they actually measured periods between, or in the 0.4 to 0.5 range. So this equation is pretty representative of the testing that has been performed. And we'll see in some other videos later on that it does well for short structures in the 20-foot range as well. So as mentioned, the period of the wood frame structure is a short period, and this equation shown here is the seismic base shear for short period structures. It's a combination of two equations in ASCE 7, 12.8-1 and 12.8-2, and this is what's most generally applicable for wood frame structures when calculating the base shear requirements. Now there are other provisions of ASCE 7 that allow lesser shear for the structure as you get higher periods, but in general this equation typically governs, and there's not much relief that you can gain by trying to take advantage of longer periods for wood structures. So to highlight a couple of the variables in this equation, R is the response modification factor within, and that's used for the calculation of the base shear. And in table 12.2-1, which was shown previously, an R equal to 6.5 applies to wood structural panel shear walls. The S sub DS is also an important term, and for those of you familiar with seismic design, it's basically just 2/3 of the site coefficient, and S sub S is that mapped spectral response acceleration parameter. So now, using that base shear equation in this table, it allows us to show a simple example of the impact of different R values on the base shear. So for a structure with light frame shear walls sheathed with wood structural panels, the R factor is 6.5, and using that equation that we just looked at previously, that we can calculate the base shear. And if you wanted to compare three different lateral systems and assume the importance factor and the site coefficient and the mapped value and the weight of the building is the same, so we're doing an apples to apples comparison, you can see the effects of the R factor, which is dependent on the lateral resisting system. So the base shear basically boils down to the effective seismic weight over the R factor. And for an R equal to 6.5 structure, that effective base shear then equals 0.154 times the seismic weight. And so the lateral force acting on the building is roughly going to be 15% of the effective system weight, which is a gravity type of load. And if we contrast that to an R equals 2 system, where you might have stucco or gypsum as your sheathing material, you see the equation results down to W over 2, or 0.5 times the seismic weight. So half the shear, half the effective seismic weight acting laterally, and you can quickly see the comparison. If you're designing with an R2 system, you have almost 3 times the base shear requirements, which is quite high, and that impacts foundation designs and number of connections and other things. So often you'll see people trying to get into the wood structural panel category just for efficiency of design and materials and management of total forces that are required in the design. Finally, if you look at the R equals 1.5 system, you see that the total base shear is almost 2/3 the seismic weight. And for those of you that have been designing for some time using the 97 Uniform Building Code, if you're in a Zone 4 area designing with wood structural panel shear walls and not in poor soil conditions, you probably had an effective shear of about 16 to 18% of the weight for shorter buildings, and for taller buildings it might have been as much as 20%. So you can see there's been quite an increase here. So let's jump then to some of the allowable story drift provisions, and ASCE 7 does include drift provisions. The allowable story drift is becoming more and more important in design and emphasized more in ASCE 7. And this equation 12.8-15 is applicable to wood as it is with other materials. The deflection that's calculated is an elastic deflection, delta sub XE, and that's multiplied by the deflection amplification factor and then divided by the importance factor. And this delta sub XE term is really an amplified deflection, delta X, that's shown here. And technically within ASCE 7, the real drift is the difference in deflection at the center of mass of the story above and below, and you'll need to see that section 12.8.2 of ASCE 7 for that. The calculated drift is compared to an allowable drift, which is then specified in 12.12-1 of ASCE 7. And for most wood frame structures, 4 stories and less, and again, if you've got a printout of the original PDF, I've added some text here that you see in red. So for 4-story and less structures, the allowable story drift is going to be 2.5% of the story height, 0.025 for risk category 2, and for taller structures greater than 4 stories, the story drift is roughly 2% of the story. And again, we'll have a little more discussion on this later on, but these are the important drift provisions in ASCE 7. So now let's change gears a little bit and talk about diaphragm flexibility. We mentioned this a little bit earlier. So in ASCE 7, as a general analysis principle, the idealized as flexible diaphragm load is distributed to shear walls based on tributary areas. This is by far the most common assumption used for wood frame structures, and it requires in general that the diaphragm is idealized as flexible, though, and you cannot distribute torsion through the diaphragm. And so what you usually end up with are structures with pretty balanced layouts of walls around the perimeters or the interiors, but not layouts that would require torsion to go through the diaphragm and to distribute forces to the walls through the diaphragm by rigid action. On the other hand, the idealized as rigid case diaphragm load is distributed to shear walls based on the relative wall stiffness. And then third, the semi-rigid diaphragm load is distributed to shear walls based on the relative stiffness of the walls and the diaphragms. And so you may want to underline the word "and" there, because that is also required in the analysis. So you'll see in future slides that ASCE 7 is going to drive wood frame diaphragms almost exclusively toward that the semi-rigid case, unless we can find a way around that. So then let's look a little bit more closely at rigid versus flexible diaphragms. And what we see in plan here is a rectangular building with 3 wall lines going north-south, and assuming they're all the same stiffness K, and there's a seismic load acting in the north-south direction, under the flexible diaphragm assumption. You see that the distribution of seismic forces to the wall lines is half the total load that goes to the center wall and a quarter of the load that goes to the perimeter walls or end walls. And that's basically the tributary area concept that we talked about earlier. But under the rigid approach, diaphragm forces are distributed to the walls on the stiffness of the walls, and we only have a third of the force in each wall. And you can see there's quite a bit of difference, at least percentage-wise, in what's required in the center wall, depending on whether you choose a rigid or a flexible analysis. So let's look again at ASCE 7, 12.3.1.1 for this flexible diaphragm condition. And there has been a change, I think I mentioned earlier, since the 2005 version, going to the 2010 version. And diaphragms constructed of untopped steel decking or wood structural panels are permitted to be idealized as flexible if any of the following conditions exist. In item A, it's in structures where the vertical elements are steel braced frames, and that doesn't apply to wood, so we'll skip over that. Item B, for 1 and 2 family dwellings, so the flexible diaphragm is broadly permitted in flexible diaphragm buildings. And then item C, for structures of light frame construction. And then again, we've got several criteria here that has to be met. That would be toppings of concrete or similar materials not placed over the wood structural panel diaphragms, except if you're less than 1.5 inches thick and each line of the vertical elements complies with the allowable story drift. And we just went over those allowable story drifts. So of these provisions here in 12.3.1.1, item C, prescribed as the flexible case, is the one that would probably most often apply to wood frame constructors that need to be designed. So that's prescribed and is not a calculation basis. And we want to emphasize that this is prescriptively spelled out here because ASCE 7 also includes a calculation method where you can calculate flexibility in 12.3.1.3, and that says that diaphragms are permitted to be idealized as flexible where the computed maximum in-plane deflection of the diaphragm is more than 2 times the average story drift of adjoining vertical elements. And here's the equation where you can see that in a graphic that tries to depict that concept. It's trying to show the wall lines displacing. That's one reference point for deflection, and then the diaphragm deflection is the other reference point there in the figure. And if you can see my cursor here, we're talking about the wall deflection shown here in this first area, and then the diaphragm deflection, which is shown here in that second area. And what people quite often find is even with wood frame diaphragms, you would expect those to be flexible when you run this calculation, and it doesn't seem to quite meet the calculated flexible case. And so if it weren't for the prescribed as flexible definition that we just talked about earlier, there wouldn't be a clear path to determine whether or not your diaphragm is flexible. So often doing this check, you'll find that your wood diaphragm does not qualify as a flexible diaphragm. And then ASCE 7 also has a prescribed rigid diaphragm condition in 12.3.1.2, and this is really not practically relevant to wood frame construction. So there's not a real clear path for wood diaphragms to be categorized as rigid under ASCE 7. So the pathway for flexible is somewhat blended between a prescribed approach and a calculation approach, and that's why the diaphragm will often be categorized in that semi-rigid category that we talked about. Now for the semi-rigid diaphragm, first of all, we're not aware of folks doing a true semi-rigid diaphragm analysis for wood frame structures. However, in some cases, folks will use something referred to as the enveloped approach, where the distribution of forces is based on both a flexible and a rigid analysis. And in the worst case distribution to each wall is what's recognized in the design. So the envelope tries to pick up the worst case distribution or the highest force to a given segment under either the flexible or rigid, and those are done independently. So you do two different checks. And if you look back at that example, that three-wall example that we looked at earlier, what you'll see is that doing an enveloped approach results in roughly 16% more base shear on that level. The worst case for the rigid analysis on the ends requires 33% of the seismic load versus 25%, and that 33% combined with the 50% that was calculated for the central wall results in roughly about a 16% increase in forces. So a rule of thumb that we've heard is that it's about a 20% more base shear requirement if you go through that enveloped procedure, but that does make it a pretty straightforward, easily defined approach. So let's shift gears again, talk a little bit about overstrength and one of the exceptions to the overstrength factor, and that's in ASCE 712.10.2.1, which has a provision for collector elements requiring load combinations with overstrength factors for seismic design categories C through F. So first of all, let's make sure we understand this is only for seismic design categories C through F. The basic provision requires that collectors and connections of those collectors be designed for load combinations with overstrength. But there's an important exception, number 2 here, that's shown, and it says in structures or portions thereof braced entirely by light frame shear walls, collector elements and their connections, including connections to vertical elements, need only be designed to resist forces using the load combination of section 12.4.2.3 with seismic forces determined in accordance with section 1210.1.1. So what's important to recognize here is that section 12.4.2.3 is the section with just basic load combinations, so there's no overstrength required. And some people may ask, well, why is this exception here for wood frame? Why not require collectors to be designed for more force? Those collectors are important elements, and if they don't function well, then load doesn't get into the walls, and so that's where your primary lateral resistance occurs in those walls. So there are a variety of reasons, and these provisions were brought into the code quite a long time ago. They're very old legacy provisions. So part of the explanation is probably that there was significant experience with wood structures where the collectors did not present a problem, and so there was that historical evidence based on past experience and judgment by a committee that developed these provisions that said that this isn't required when those new overstrength provisions were brought into the code. But if we look even further, there are probably a few other reasons why this is not problematic. One, the wood member itself has design values based on very low percentile estimates of overall strength. So by the way the wood design values are established, the collectors, which are often going to be double top plates or rim boards or band joists in your floor wall system, already has a bit of overstrength just in the product themselves. So they're pretty decent safety factors on those products, and accordingly or likewise, the connections also have significant safety factors. Bolts and lag screws in particular have very high safety factors, and while the safety factor for nails may not be quite as high as what you might see for bolts and lag screws, the nails tend to be very ductile. So we don't see brittle failures in collectors, rather we see a stretching of the element as it overloads. And finally, in a wood frame diaphragm system, the panels themselves, as they're connected to the wood frame members, while they're not designed as the cord, they're designed to transfer shear forces. They really don't know that they're only supposed to transfer shear, and so they're probably giving some strength as well that's not accounted for in the system, or the system effect. So let's talk a little bit now about redundancy, and that's section 12.3.4.2 of ASCE 7, and we think those first came into the 1997 UBC, and those have evolved over the years. And so in ASCE 7.10, you see there's special treatment given to light frame shear walls with regard to this redundancy factor. And generally, for this redundancy factor, if you do absolutely nothing, you don't want to think about it or do anything else, you can use a 1.3 factor. So if you don't want to worry about any additional considerations, you can use 1.3 to increase your base shear and continue with your design. Otherwise, there's some fairly complex provisions in ASCE 7 that discuss the removal of an element to see if you create a torsional problem with removal of that element. So there are two important exceptions. One is if your light frame shear walls, you don't need to remove an element with an aspect ratio of 1:1. So if you have a structure that's entirely composed of longer width walls or low aspect ratio walls, there's a pathway to say that the redundancy factor equals 1. Other than that, this item B is probably the most common pathway and easiest to apply to determine if the redundancy factor is going to be 1 or 1.3. And it reads that structures consist of at least 2 bays of seismic force resisting perimeter framing on each side of the structure. The number of bays for a shear wall shall be calculated as 2 times the length of the shear wall divided by the story height for light frame construction. So what we've tried to illustrate here is that a shear wall line, we have a shear wall line, and we're going to try and figure out if it qualifies as 2 bays. So applying these ASCE 7 provisions, the number of bays will be calculated as 2 times the length of the shear wall divided by the story height. So in this case, on this wall line, we have a length of 4 and 6 feet, so that totals 10 feet shear wall. And 2 times 10 is 20, and then we divide 20 by the story height, which is also 10 feet, and that results in the number of bays equaling 2. Now, what would appear somewhat ironic here is if you had 2 shear walls that were each only 4 feet long, you can't calculate 2 bays. So if you had 2 4-foot walls, the total there is 8 divided by a story height of 10, and you do those calculations, you come up with 1.8 or 1.6 and not 2. Either way, it's going to be less than 2. So you can see then that the number of bays is going to be strictly a function of length and story height. So that's a quick overview of the redundancy provisions. Then we move to horizontal combinations, and there's a provision in ASCE 712.2.3.3 that will permit you to have multiple lines of resistance composed of different materials, and this may or may not be advantageous. This can be somewhat complex, but there may be some structures where this makes sense. So let's highlight in this figure here the seismic load, which is running, let's say, in the east. We'll call the east-west direction, and we have 3 lines of resistance. We got 2 exterior walls and then 1 interior wall here. And let's say that on the exterior walls we've got wood structural panels, and on this interior wall we've got gypsum. And so the exception to ASCE 7 would allow here the design of load in the exterior wall lines equal to 6.5. And then the gypsum line would then have an R equal to 2. And this approach is only permitted for risk category 1 or 2 buildings, and it needs to be 2 stories or less, and light frame construction, flexible diaphragms, and the diaphragm based on the least R, not the greatest R. So there may be cases where you have a central corridor that has a long enough length that there's enough gypsum to handle the shear, but that's going to take some additional calculations there that you'll need to decide whether or not that's worth the effort. So this is related to ASCE 7, and this is the horizontal combination of shear using dissimilar materials. So ASCE 7 actually refers you for part of this to the wind and seismic provision, so this is going to add another layer of complexity. And this figure is identical to the one that we just looked at, except for the for this southernmost wall, we're going to add gypsum to the inside wall there. So now we've got wood structural panels on this north wall. We've got gypsum by itself on the center wall, and then wood structural panels on one side and gypsum on the other side of the south wall. So we're going to hypothesize that somebody wants to use the combined strength of wood structural panels and gypsum. Maybe they're just short on their capacity and want to try and bump that up. And the wind and seismic standard permits you to consider different materials for different sides of the wall. But there is a specific rule if you're going to do that you have to establish the unit shear as the shear of the larger side, or the larger shear, or 2 times the smaller shear. So let's say that the wood structural panel on one side has a unit shear of 300 PLF, and the gypsum on the other side had 100 PLF. So you'd be permitted to take 2 times the gypsum, or 2 times 100, and design for R equals 2. But it's really, doesn't seem like it's that advantageous to utilize this rule in a lot of cases. I mean, I can see cases where you might have a lot of gypsum and you want to use the capacity of the that stronger side with R equal 2, where that may be helpful. But if you're using this summing rule, it's being relied on for shear resistance, and so the R value in that case would be 2. So, and there's also a seismic limit associated with gypsum, which would be seismic design category D. So, on the other hand, if you were to just use the wood structural panel only, your R value is 6.5, and so you'll have to decide, again, looking at your specific situation, whether it's advantageous for you to use this approach. So there's some additional resources where this is discussed, and I have to give also some credit here for this presentation, originally developed by Phil Line, and he and Jim Russell did a paper in Wood Design Focus back in the spring of 2006. You can download this paper free from our website as well, but it deals with this issue of redundancy and horizontal combination and dissimilar materials, and so this will be helpful for you as well. I also want to continue to mention throughout the program that the commentary to the Wind Seismic Standard is a really good resource as well, and so you might want to look there if you've overlooked the fact that that commentary is built into the 2008 Wind and Seismic Standard. It's in the back and is keyed to specific provisions of the Wind and Seismic Standard itself. So ASCE 7 12.2.3.2 also has a 2-stage analysis procedure, and this is commonly used on structures that look like this. This is a 5-story wood frame over 1 story of concrete podium, and so this 2-stage analysis procedure has some qualifiers as well, and we want to emphasize a few of the rules that go into this, and that is that the base is rigid relative to the top, and what ASCE 7 requires, and the revision in ASCE 710 makes clear, is that the height we're looking at here is the structural height of the wood above the podium. And so from the base, which you see labeled here in this drawing, up to, in this case, since we have a pitched roof, the average roof height is how you would measure the structural height of the building, and that's a very important clarification to ASCE 710. There's really no change in ASCE 7 provisions for horizontal separation of buildings other than new numbering. It goes from 509.2 to 510.2, and again, that structural height term was clarified as being measured from the base. So this kind of gives you a sense of that provision is spelled out in ASCE 710. Another thing to reiterate is that for light frame, the structural height limit is 65 feet. So, and there again is that new provision that defines structural height in ASCE 7-10. There again are some additional resources for multi-story wood frame over podium type construction, and there's a really good 5-story wood frame example by Doug Thompson available on the Woodworks website, and there's also a case study by APA 110, all wood podiums in wood-rise in mid-rise construction. So there's some additional resources as well. I'm pretty sure both of those resources are free to download from the respective websites. So let's look briefly then at the ASCE 7 simplified procedures. It's applicable to 3 stories or less, occupancy categories 1 and 2, and up through seismic design category D. Some of the benefits, we don't have to go through the normal triangular distribution. We just have simple factors based on 3-story, 2-story, and 1-story conditions. There's no required check of drift, which simplifies things. Diaphragm forces are also based on effective seismic weight on each level, and that also simplifies things greatly. One of the drawbacks here is that there is a checklist that you have to meet in order to use it, but the most onerous provision is the one about torsion. But if you read it carefully, and if you're idealizing your diaphragm as flexible, then you need not apply that particular provision. That has often been a criticism of the simplified method, but it's a non-issue if you're idealizing your diaphragm as flexible. And finally, for diaphragm anchorage to concrete and masonry structural walls, there's a case where you have a wood. If there's a case where you have a wood frame diaphragm anchored to concrete or masonry, you have provisions that have been in the code for some time to make sure the wood diaphragm is properly tied to the concrete or masonry wall to avoid a failure of the diaphragm. And an important detail is this one right here. And that's to make sure the wood diaphragm is properly tied to the concrete or masonry wall to avoid failure of the diaphragm. This strap goes directly from the concrete or masonry structural wall into the wood framing. The older detail that was shown was problematic because with sheathing attached directly to the wood ledger, we'd get cross-grain bending, and that led to some failures that we saw in some seismic events. So this is a way to remedy that situation. Again, some additional resources that are helpful here. APA has a publication Z350, and FEMA 547 has some information as well that's helpful in this regard. So I'm going to ask Marcy, if you would, to come back and help us with another poll.
Absolutely. All right. It's a true-false question. So a diaphragm may be idealized as flexible where the maximum deflection of the diaphragm is greater than 2 times the average story drift. Is that true or false? All right. About 28% have voted. So All right, I'm going to go ahead and close the poll and then share the answer. 88% say that's true and 13% say it's false. And then, Buddy, I'm going to let you share the actual answer.
All right, so the actual answer is true, and looks like everyone's been paying attention, so very good. I'm going to now ask Michelle if she'll join us and
Unmuted.
take over here for a while and take you through the next section of the